Now, after we spoke a bit about classical mechanics, let's come back to the Langevin equation that we discussed before. We have discussed the Langevin equation, how it was initially produced, and how it generalizes the Ito diffusion that is more conveniently, conventionally used in finance. We also saw how the stochastic differential equation arising in our formulation turns out to be a particular type of the Langevin equation with a nonlinear drift with metastability, with potential metastability. Now the Langevin equation is a pathwise equation for a particle. It's driven by a particular realization of a noise term along a path. But for some problems, this formulation is not the most convenient one, and instead a probabilistic description of a system is preferred. And this can be done starting with the Langevin equation, and this transition leads to another famous differential equation. This time it's a partial differential equation, or PDE, known as the Fokker-Planck equation. And in finance, it's also sometimes called the forward-Kolmogorov equation. This equation is equation 42 shown on this slide. It describes the probability for a particle or a system of particles or any other stochastic system to be in state x at time t, given that it was at some other state x naught at previous time t naught. So in this equation we have a time derivative of the probability density p of x, and in the right hand side we have two derivative terms. The drift term contains the derivative of the potential u prime, and the second diffusion term is a second derivative term that depends on the volatility function sigma of x. In our case, sigma of x equals x, that is, we have a proportional volatility function. This equation should be solved under an initial condition given by a delta function shown on the bottom of this slide. Now, if you want to understand how the Fokker-Planck equation is derived from the Langevin equation, here is a sketch for you. Let's consider some function f of x of the state variable x and consider its expected value. We will denote this average by the left and right brackets. So one way to compute the time derivative of this expectation is to take the time derivative inside the brackets and then use Ito's formula. And this gives us the first line in the first equation on this slide. On the other hand, we can also replace the brackets by explicit integration with the density p of x, and this gives us the second line in this expression. On the other hand, we can compute the same quantity differently by recalling that the mean of the function is given by its integral with density p. And because f of x does not depend on time explicitly, where we differentiate such integral, the time derivative applies only to the distribution p of x. And this gives us equation 43 on this slide. Now, if we integrate by parts twice in the first expression, we obtain equation 44. So we obtain two different expressions for the same quantity, which we can now write as equation 45 here. But because the function f of x that we used in this derivation was arbitrary, the equation should apply to its integrands and not just to the integrals on both sides. And this produces the Fokker-Planck equation. Now, the Fokker-Planck equation is a second-order partial differential equation, and it should be supplemented by boundary conditions in addition to an initial condition. And the most interesting boundary is the boundary at 0. This is the default boundary, as we already discussed earlier. If the stock price touches this point, it stops moving. And this follows from the form of the SDE for our model, because both the drift and the diffusion terms vanish at this point. And this is called a natural boundary in classifications, in the classification of differential equations. If the sign of the derivative of the drift potential is negative at this point, it's called an exit boundary. Now, if we look at the GBM model, the point x equals 0 is also a natural boundary for this diffusion, for the same reason that both the drift and diffusion vanish at this point. But a big difference between these two cases is that in the GBM model, the boundary is unattainable. This is something that we already discussed in the last week. If we agree to call default events of a stock price when the stock price drops to 0, then such events are incompatible with the GBM dynamics, creating all sorts of problems. But with the nonlinear diffusion, such as one obtained with our framework, such events are perfectly possible. In other words, a natural boundary at 0 is attainable in our model, and it becomes an absorbing boundary. Once a stock gets there, it will stay there forever. In other words, we do not have to enforce correct behavior of the model by imposing absorbing boundary conditions at 0 by hands. The system knows that once it reaches this point, it will stay there forever. And this is called absorption at 0, but without enforcing specific absorbing boundary conditions at this point. So what might happen on this graph is that a particle initially to the right of the potential barrier, denoted as the rightmost red point here, can go over the barrier as a result of thermal fluctuations. Then it stays in the left well as the red point on the left of this graph. Now, when the particle is there, touching the barrier at 0 becomes much more plausible event because there is no more barrier to cross. And this scenario can therefore describe stocks that are in nearly free fall to bankruptcy. Still, there is a chance for such stock to go over the barrier back to health, but such double jump would be a very unlikely event. Now, instead of analyzing things in the X space, which is a space of market capitalization or of a stock price, we can switch to log price, y equals to log of X. And the main reason why such change of variables makes sense is because it changes the multiplicative noise into additive noise. And additive noise is much easier to work with because it affects classical dynamics much less than a multiplicative noise. So if we change the variable in the Fokker-Planck equation, then in terms of the log price y, the equation now takes the form shown here in equation 47. And there are two major changes that relative to the original formulation of the equation. First, the diffusion term now has a constant volatility. Second, the drift potential now goes unbounded to the negative infinity and becomes negative infinity there. And this means that in the log space, a fall to the center can be seen as an infinite escape to negative infinity. Because we changed to log price, the absolute 0 is now at infinity, where the new potential also has a singularity there. But this approach is convenient because we can approach the singularity actually as close as we want, using the y space. And finally, I want to discuss what happens in the Fokker-Planck equation in a zero noise limit. If we take it to the log space and set sigma equal to 0 there, we get equation 48. Now you can use this equation to compute the time derivative of u using the chain rule as shown in equation 49. And this shows that this derivative is always negative unless the system reaches the point where the derivative vanishes. But note the interesting fact here that this equation only seems to require that the derivative vanishes, but not necessarily whether it's a minimum or a maximum. And to settle on the right minimum, we actually need noise in the system.